All right, I'll begin. Heavenly Father, we thank you for this day. I thank you for these students. Just pray you be with us today. Help us to glorify you in what we do this day, Lord. In your name I pray. Amen. So, before I forget, let me close those back doors. Otherwise, there's always a certain amount of hall noise in here. So today, we are in chapter 4. Thanks. Much appreciated. So, chapter 4, we begin our study of dynamics. All right? So, dynamics. What's dynamics? Basically, study of force and motion, okay? So the basic tools we have here are, well, Newton's law. So what's Newton's second law say? It says, what does it say? It says that the mass times the acceleration is equal to the net force. Right? So mass times acceleration is equal to the net force. The net force is a vector, the acceleration is a vector, and this is Newton's second law. All right? So, for example, if the acceleration of an object is 0, what's that say about the net forces on it? Yeah, the net forces are 0, which isn't to say that there's no forces, it's just to say that all the forces which are acting on the mass cancel out, right? Like you guys, some of you have done the force table lab, right? That's all about forces canceling out, right? So we're in equilibrium. You know, you find that equilibrium and all that fun stuff. Don't get me started on the G newtons. All right, so this is a joke for those of you who are in my lab. Newton's second law. What's Newton's first law? What's Newton's third law? What are the other laws? What's the first law? What does it say? An object, how's the usual lingo go? An object at rest will remain at rest unless acted upon by an outside force. Or the more nuanced statement of it is an object moving in constant velocity will stay moving at that same constant velocity along a straight line in straight rectilinear motion unless acted upon by an outside force, right? This is Newton's first law. So, all right, well that's the first law. I don't even want to write it down. What's the third law? What's Newton's third law? It says what? For every action, yeah, there's an equal and opposite reaction. So it's talking about forces. It says that forces come in pairs, right? For every force, there's a corresponding reaction force. And we'll get back. Newton's third law is a little bit more subtle. I think Newton's second law is a good place to start, and let's work on that for a little bit, okay? So, example 1. Suppose we've got a box with mass m, all right? And suppose you got some Mr. Top Hat here, and he pushes on it with a stick, like so, right? And he pushes on that box. And by the way, this is ice. Not even ice. It's silicon. I don't know. It's a magic frictionless surface. Okay, magical frictionless surface. You don't want to try to. You definitely don't want to try to stand on this surface. It wouldn't go well for you, right? Right? Ever try to stand on an ice rink? I mean, you can still do it because there's actually still some friction, right? But if you can imagine really being on a perfectly slippery thing and then like trying to stand up, It wouldn't go well. So anyway, friction of the surface, and he pushes on it. Let's say with this force, I'll call it F naught to give it a name, and let's say of 10, well, how about 100 newtons, right? What are the units for force, by the way? So it would be the units of mass times acceleration, which is what? If we use SI units, we've got what? Kilograms times meter per second squared. This is so important, it gets a name. This is called a Newton. A Newton is a kilogram meter per second squared. This is the natural unit of force in the SI system. So suppose we've got 100 newtons pushing on this box, and that's all that's going on. It's a friction on the surface. Actually, that's not all that's going on, right? Because I do have in mind that this is on the surface of Earth, right? I mean, I have that in mind. So, what's actually going on here? I've got too much in my picture right now, but I'm gonna draw a picture of the same thing again over here. I'm gonna draw what's called a free body diagram. All right. So the free body diagram here looks like what? Well, we're given that there's a F naught of 100 newtons, right? What do you guys want the mass of this box to be? How about 50 kilograms? Sound good? We'll think about it being 50 kilograms. So can you guys, if this is on the surface of the Earth, well, there's other things at play, right? What else? Yeah, there's gravity. So gravity does, which way does gravity go? Down, yeah. And this is the weight, right? Down, yes. No, the box is sitting there and it flies up into the, yeah, no. Okay, yes, down. Gravity should go down. That kind of defines down, right? So this is mg. That's the weight of the box. But there's another, now actually I said I was going to wait to talk about the third law, but this is a good, well, I mean, this third law is in action here in some sense. Because there's a what? What else is there? Gravity, for example, for me, gravity acts on me and through my shoes, the force of gravity acts on the floor, right? But what does the floor do? It pushes back up on me, right? That's the so-called normal force. So there's a normal force, which I will use the symbol F sub n for in the interest of not confusing you guys with newtons, all right? Sometimes I just use a capital N for normal force, but that's probably a bad idea, yeah. We will talk about friction soon, but not yet. Okay. Tell you what, I'll put friction in example 2. All right? So this is the so-called free body diagram. Are there any other forces at play on the box? No, I said there's no friction, right? So that's kind of it. So as you look at the net force, what do we have? Well, we've got, I mean, if you look at it, 0 Fn, that's the normal force, plus 0 comma minus mg, right? And then how about what's the other force at play here? 100 newtons. So my point is that these two are vertical, and that's a horizontal. But we don't usually write it like this in here. Typically, when working in 2 dimensions, we just write 2 separate equations, one for the x components of the force and one for the y components of the force. So the way I usually would express this is something like in the y, we have the net y component of the force would be the normal force, whatever that is, minus mg, right? And in the x, we have the net x force is what? It's just equal to apparently 100 newtons because I said so. Now, so this equation right here, guys, the Newton's second law, that's a vector equation, right? So that means two things. Oh, I'm sorry. Yeah, because 2 things, because your book is primarily 3-dimensional, right? I mean, sorry, two-dimensional, because the world is two-dimensional, right? The world is not two-dimensional. But your book is very much two-dimensional, right? I mean, I don't know. I have a hard time finding this third dimension in your book. But, I mean, so truth be told, this is really max equals to the x component of the force, may, equals to the y component of the force, maz, equals to the z component of the force. I mean, that's the truth. Because physics is three-dimensional, because for the most part, we live in a three-dimensional world, right? But we like to work problems in here which are specialized and idealizations, which we can think of as two-dimensional, because math is much easier in two dimensions, right? So we're going to focus on two-dimensional problems, like my first example, but I feel obligated to tell you that physics is three-dimensional. This should not be controversial that I'm telling you this. Anyway, focus on these two. In this situation, what can you tell me about the acceleration? I can tell you right now that the acceleration in the x direction is going to be positive, right? Pushing on the box, going that way, if that's the positive direction, certainly the x acceleration is going to be positive here. How about the y acceleration? That's right, the y acceleration is 0. See, this is the situation is we're essentially in equilibrium as far as the y motion is concerned, right? To say that the acceleration in the y was not 0 would be to say that the box was either accelerating off the plane or into the plane, which would be very weird, right? So in contrast to the lab 2 that you're doing, this has acceleration in one direction but not the other. Lab 2 had, like, it was an equilibrium situation, right? The total acceleration, both x and y, if you think about x, y being in the plane of that force table, they're both 0. Okay, anyway, getting back to the point, this is equal to 0, and this is equal to mass times the acceleration. I mean, you could put a sub x on that if you want, because it's the x component of the acceleration, but you could just say acceleration here, because it's also the magnitude of the acceleration. Anyway, so what's the normal force in this situation? We find that the normal force is equal to mg in this case, and that was what, 50 kilograms times 9.8 meters per second squared, which is 49 newtons. So the normal force happens to be 49 newtons in this case. All right, I think. Did they do the math right? I think I'm okay. And how about the acceleration? What's the acceleration here? The acceleration in the x direction is 100 newtons divided by the mass, right, which is 100 newtons divided by 50 kilograms. What's a newton over kilogram? Well, if you look at it, a newton over a kilogram is a meter per second squared, right? So this is actually 2 meters per second squared. So there's a couple of interesting things to calculate from this example. We found the acceleration is 2 meters per second squared, and also, you know, the normal force is equal to the weight. Question?
Is that 50 times 9.8 or 5?
50, because the mass is 50. Oh, yeah, that seems reasonable. Thank you. Do any of you know anyone taking my abstract algebra class? This is the time I would say something about all my mental energy has been spent making their test for tomorrow, and then you could tell them that, thus, you know, inculcating the culture of fear that should surround my test that's going to be given tomorrow, right? It's a senior level math class. There should be a certain amount of trepidation, right? In contrast, your test is a 200 level physics test, which will be shockingly like your homework and class examples, all right? I have no axe to grind in here. I just want to make sure you understand the basics. Any questions about this? So let's add friction. Suppose we, again, push with F naught. But this time, let's suppose that there's a friction force. Force of friction like that, right? Now, force of friction is a complicated thing. Because there's two kinds of friction, all right? There's kinetic and there's static friction. Let me illustrate. Oh. All right, so static friction is like this. I'm pushing on it right now. I'm pushing. Can you tell? You can't tell. It's still in equilibrium, isn't it? I'm pushing, and then all of a sudden it starts moving, right? So static friction will oppose a whole range of forces up to some critical breaking point where you break free. Once you break free, then you're in the kinetic region. And in the kinetic region, the force of friction kinetically is about constant. Once you start moving, a good approximation to the way things skid is it has the same friction force as you move. This is a lie. Of course, there's a velocity dependence. If you move faster or slower, it's more complicated. But as a good starting approximation, there's something called the coefficient of kinetic friction. That's going to be the situation here. This block is moving. We're going to have to use kinetic friction. All right? So kinetic friction is a characteristic of the surface you're looking at. So mu sub k times the normal force. This is the formula for kinetic friction. And you can look up the coefficient of kinetic friction for different materials. Let's just say that this has a coefficient of kinetic friction of 0.8. I think rubber on a dry road has a oh, that's a static situation. Shut up. All right, so let's suppose that the coefficient of kinetic friction rather is about 0.8. All right, same force, same mass. What's the difference? So again, the vertical story here is rather boring. We've got the normal force. We've got old habits. That's not even a word. Old habits. Habits. So this is a bad habit, I say, because N is newtons, right? So like I should not use that symbol for the normal force, should I? No. Let us use F sub N for the normal force in the interest of not confusing you guys, okay? And me. F sub N is the normal force. Maybe your book has something else, and if you want to use what's in the book, more power to you, all right? I wouldn't deny that to you. All right, but so in the vertical, what do we have? We have 0 is the acceleration, right? And that's going to be the normal force minus mg. So again, the normal force is equal to mg. This is not always the case. My example 3, we will have a normal force which is not equal to mg, all right? So horizontal, aka x, right? So what do we got? We've got ma is equal to, what's the forces? We've got 100 newtons minus the force of friction, right? You see why the minus? Because it's going the opposite way, right? So we write down equations, they should have opposite signs if we set up our equations right. Okay, so then what? So this gives us that acceleration is equal to 100 newtons minus the force of friction. What is the force of friction? Well, we can calculate it already, right? We've got 0.8 times the normal force, right? What is that? Apparently, it's the same as last time, right? It's still 490. Yes, 490. Yes, okay. 490 newtons, which is what? Is that my calculator or is that your calculator? It's your calculator. No, it's okay. It's okay. I actually remember to bring my calculator today, so let me. I know you guys just told me, but it'll make me feel better to feel like I brought this for a reason. All right, 392 newtons. There you go. That's the force of friction. So the what Oh, no. Oh. What's the problem with my example? You know, this is one of the differences between physics and math. In an algebra section or a calculus section, I can pretty much just write down problems and ask questions, and it's very rare that the problem is just unreasonable. This is an unreasonable problem. We do not have 100 newtons is not enough to overcome to keep it moving, right? We need at least 392 newtons, a little bit more than that, to keep this thing moving. So how can we fix it? Add a 0, change the 1 to a 5. I mean, you got choices. I'll change the 1 to a 5, if you don't mind. So the way this problem might appear on the test is a person, pushes on a box with 100 newtons. The coefficient of static friction is what it is. Will the box keep moving? The answer is no, it can't. There's not enough force to overcome there's not enough to overcome friction. Now, if I put 500 there, then we're good. See, because then I've got 500 newtons minus 392. And so what, that divided by the acceleration, right? Excuse me, divided by the mass, which was what? 50 kilograms. So what's that give us? 108 over 50, Newton over kilograms, also known as what? Yeah, meters per second squared, but I would take that, but I mean, I should just take it, but I'm still trying to convince myself it was worth bringing my calculator today. See, my calculator is a sarcastic little thing. It's like 54 over 25. Does the answer in here, should it ever be 54 over 25? No, this is not a math class. This is not a useful answer. For us, we hit the S to D button, and I get 2.16, which you told me like a minute ago. So 2.16. We'd like decimal answers, yeah. 2.16 meter per second squared. There you go, that's the acceleration. By the way, going back to my original problem, what if I had made this one 500? What would have happened? If you increase the force by 5 times, how much does the acceleration increase by? 5 times, right? There's a direct proportionality because F equals ma. Okay? Or more to the point, A is equal to F over m. So if we had, this would have been 10 meters per second. 10 meters per second squared if we'd done 500 newtons. As you can see, friction slowed it down quite a bit, right? Yeah. Question? Oh, okay. Yeah, I know it's hot in here. Let's see here. All right, so the first 2 examples I've given you in some sense are a little bit misleading because they might tempt you to think that the normal force is always just the weight of the object. That's not often it's not the case. So let's look at example 3. And this time, I'm going to have, again, a coefficient of kinetic friction of 0.8, let's say. So suppose this is a situation. We've got a box, all right? And this time, he's pushing on it like this with his cane or whatever, all right? He's pushing on it like that at an angle, right? And let's suppose that this angle here is, I don't know, 30 degrees. So suppose he's pushing on this box at an angle of 30 degrees. We have friction, because you guys want me to put friction in the problem, great. Actually, it's probably helpful for us to just not do friction to start with on this example. Okay, let's not put friction in here to make it slightly less complicated. So frictionless again, okay? Then the question is, okay, so if he's pushing on with this cane, applying a force of, say, F naught equal to, let's say 100 newtons again, right? And this is a mass of, I don't know, 3 kilograms, right? My question then is, and that's not where I want to write that, because I want to make a free body diagram up there. So my question is, what's the acceleration of the box in this situation? And also, what's the normal force in this situation? So what are the forces at work here? There's the cane force, the force he's pushing on the box with his poking stick, which I could, look at like this. But there's also what? There is the normal force. And what else? There is mg, right? The length of these arrows is not significant. This is just a heuristic to guide the calculation, all right? So in this situation, what we need to do is we need to break up that 100 Newton pushing force into its x and y components. How do we do that? See, only this part of that 100 newtons, this part right here, right, is actually leading to acceleration horizontally. The other part of that 100 newtons is just pushing down, right? So it's essentially, it's making its effective weight bigger in some sense, right? That red arrow. It adds to mg in the vertical direction, right? So if this is 30 degrees, this is 30 degrees, right? And so that makes this 100 newtons times the sine of 30 degrees. The sine of 30 degrees is a half, so we've got 50 newtons like this way. On the other hand, how about the green? What's the green? The adjacent side, right? So this is going to be 100 newtons times the cosine of 30 degrees, which is, to a good approximation, 86.6 newtons. Because cosine of 30 is like square root of 3/2, which is about 8.86-ish, something like that. Great. So now we can write our horizontal and vertical equations for Newton's second law. And so vertical, we've got 0, right, is what? It's equal to, well, the normal force, old habits die hard. The normal force minus 50 newtons minus mg, right? Does that make sense to you guys, what I'm saying? So this time the normal force is not equal to the weight. It's the weight plus 50 newtons, right? So the normal force is equal to what? What's mg here? Yeah, so, 3 times 9.8. $29.4 newtons, yeah? So we've got 50 newtons plus 29.4 newtons, so the normal force is in fact 79.4 newtons. In fact, the normal force is almost 3 times as large as it would just be by its weight alone here in this situation, right? Which means if we added friction to the mix, the friction force would be almost 3 times as big with the cane pushing on the box as opposed to with it out pushing on the box. Or like if I pushed on the box with this cane horizontally, the friction force would just be from the weight alone. It'd be smaller. If I push on the box at an angle, then I'm effectively increasing the weight and thus the kinetic friction, so it's harder to push. You know this, right? I mean, if you try to push on a box like this, it's hard. If you can kind of get down at the level and push like that, it's much easier, right? If you've done this sort of thing. It's also much easier to push out your back. But anyway, horizontal. So we have the mass times the acceleration we're trying to find is equal to what? What's the x component? What is the only x force involved here? The x force. It sounds very exciting, right? Are you guys fans of the x force? No? I put the x force in green. It's 86.6 newtons. That's part of the pushing force, but not all of it, right? And we needed trigonometry to figure out what that was precisely. So the acceleration then is 86.6 newtons divided by the mass, which in this problem I made 3 kilograms. I've used my calculator enough today already. I'll let you tell me. 28.86. 87. Meters per second squared, yeah. Any questions about this so far? I'm sorry about the hurricane. It's unfortunate that we couldn't have made it to class and met that day. A little bit behind my schedule because of that, right? So let me explain what that means. That means I will not ask a question about relative motion on the test. That's what it means. All right, the show will go on. I'm just essentially dropping relative motion from your test. Sorry about that. I do love that topic, but we have a finite amount of time in here, and the show must go on. Any questions about this? All right, well, you're like, well, I'm starting to feel comfortable with these questions. This seems like, I mean, there's easier versions that you don't need all this drawing I'm doing, right? If I tell you you've got a race car and it develops a force of 1,000 newtons, right? And I tell you that the mass of the car is, 200 kilograms. That's a really light race car. What's the acceleration of the car? If you've got a force of 1,000 newtons, its mass is 200 kilograms, what's its acceleration? You take 1,000 newtons, divide by, what did I say, 200? You get 5 meters per second squared, right? Which is not bad. That's about half a g, right? What can your car do? Like how many g's? Do you guys know what a g is? If we take these accelerations that we're finding and we divide by 9.8, that's the number of g's. Like in terms of g's, this is a equals to, I'll tell you in a second here. You take 28.87 divide by 9.8, and it gives me an exact fraction, of course. 2.946 g's. See, 2.946 times 9.8 gives me 28.87. I don't need units in this case because g is a number which already has units attached to it, right? G is 9.8 meters per second squared. Contrary to the impression you might get from lab 2 in your lab book, which would seem to indicate that g is 9.8 as a pure number, which is nonsense. Sorry, I will get over it eventually. I shouldn't teach lab, it makes me angry. Anyway, you're like, well, why don't you just write your own lab book? I do not have unlimited time, people. I tried to one summer, actually. I tried to start writing a lab book. I brought all the labs home in my garage. We started thinking about writing the labs. And then I realized it was really, really boring. So I decided to do other things, like play with my kids. So, yeah. But somebody should write a lab book. Maybe one of you guys should do it. It's waiting to be done. All right. That'd be a great honors thesis or something, right? Oh, I know. Okay, so next problem. Let us move on to pulleys. Let's talk some about pulleys. So what's a pulley? What's that? Pulley's in tension. So, you know, if this is something like this, and if this is a mass m, right, and and he, you know, there you go. Don't question it. So he pulls down. If Mr. Top Hat here pulls down with a force F naught like that, what happens? How's it work? So the third law says that the rope pulls back on him with a tension T, right? So there's the rope pulls back like this, tension T. But then, of course, how it works is if the rope does not stretch, that same tension, right, what happens? It goes over the pulley, right, over this wheel, and it goes back down here, and the rope will end up pulling on the mass with that same tension T. That's what ropes do. They give us a way of pulling on things, yeah? So whatever, if he pulls on the rope with force F naught, this T here is not helpful. Let me just get to the point. If he pulls on the rope with force F naught, then it goes up here around the pulley, and then it turns the force around essentially, right? And then the rope pulls on the mass with tension T upward. That's the deal. So if that's the situation, what's Newton's second law for the mass? We have mass times acceleration is equal to, well, tension. Does that make sense? And I don't really need vectors here, right? We're just talking about acceleration in the what? In the y direction, right? You can say the x acceleration would be 0. So why bother writing it? It's not needed here. So if you understand that, the next thing to do is to put two masses over a pulley, right? See how that works. So what if we put a pulley and we have two masses, M1, M2, like that, right? We're assuming that the rope does not stretch and that the pulley is frictionless. And what that really means is just the tension stays the same. So what I'm trying to say is that the rope pulls up on this mass with tension T, and it pulls up on this mass with tension T, and those tensions have to be what? Equal. They're the same tension. It's the same rope. But what are the other things at play here? How about the force of gravity? What's it look like? See, now we have two masses. We can think about two sets of Newton's laws. We have the Newton's second law in mass 1, right? Which is also going to have m1g down like that, right? And we have Newton's second law on m2, which is going to have a weight which goes like that, right? And so you think about it, we've got mass 1, the acceleration of the first mass, right, is equal to what? Looks like, right. So we've got a, so you guys give me a choice. Do you want, which mass do you want to be larger? M1 or M2? There's not a clear consensus here. What's that? 1? All right, 1 it is. So we're going to assume that M1 is greater than M2. So common sense, which way does, which one falls? M1, right? M1 falls. So the motion's going to be like this. So what's the natural choice of positive? The natural choice is to choose the direction of motion as positive. That's just a choice. You could choose either way as positive, like that's just setting a coordinate system, right? But if that is the positive direction, then that makes this a positive force, right? If this is positive direction, like that. So M1A1 would be M1G, and then tension is opposite that direction, that motion, so minus T. What about Newton's second law for the second? Well, it's m2, the acceleration on the second mass. And in this case, see, in this case, tension's going in the direction of the motion, right? So this time I do plus t, and I do minus, see how the tables have turned over here? m2g. Now, at this point, you'd be like, but we don't know what tension is, and we don't know what acceleration 1 is, and we don't know what acceleration 2 is. This is rather troubling, because we have 2 equations and 3 unknowns, which is not good, right? But what else do we know? If the rope doesn't stretch, what can you tell me about the acceleration of 1 and 2? How are these related? If this rope is not stretching, the motion is coupled, right? This one goes up as fast as that one goes down. So I would suggest that we say A1 equals to A, and A2 is equal to what? Oh, I have a moment of doubt. I'm going to put a minus a there, and if it makes everything crazy in about 3 minutes, we're going to give up on it, okay? But I think that's supposed to be minus a. I will admit, I have a moment of, So my point, guys, is that we've got m1a minus m2a, if I'm right about it. And so with that, we can add equations, right? We can add equations. And when you add equations, we get m1 minus m2a is equal to m1g minus m2g, because the tensions cancel. Okay, at this point, I know I wasn't supposed to put the minus there. So this was just supposed to be a. My apologies, guys. There's no minus here. That's nonsense on my part. So sorry.
Where did the A come
There's no, that minus is bogus, and this minus is bogus. We just have that both accelerations are a. So sorry. I've already accounted for the signs in putting the pluses and minuses as I did in the force formulas. That's what was confusing me. Putting a minus there as well is like double counting the direction in some sense. Yep.
Where did the A come from?
Oh, my point is that because the rope is not stretching, the motion is coupled. So whatever the acceleration is of this, it's the same for that. Like they're moving at the same rate if the rope is not stretching. If they had different accelerations, that would mean the rope would have to be tearing or stretching out, which we don't allow. Yes?
This may sound silly, but is there a way like A2 would be like A squared?
Oh, A2 would be A squared. No, I don't think so. But this is supposed to be I mean to add these equations. That's a plus. Listen, I knew that what I did was wrong because I was about to solve for the acceleration, and I would have had m1 minus m2 in the denominator, which would have been divergent. It would have blown up when m1 equals to m2. But when m1 equals to m2, that shouldn't make the acceleration go to infinity. It should just make the acceleration go to what? When the masses are equal, what happens? Nothing, right? They just balance. Unless you give one a tap, at which case they'll keep going at constant velocity of motion with no acceleration, but they'll keep going, yeah? This is actually one of your labs that you'll do later, okay? So anyway, solving for A, we have the acceleration is m1g minus m2g divided by m1 plus m2, and there you go. This is the acceleration for such a system. This is a pretty standard example. It makes a lot of sense, right? When the masses are equal, the acceleration is 0. What would happen? What happens if one of the masses is way, way, way bigger than the other? What should happen? Like if what's that? The acceleration should increase. I think that's not wrong. What would happen if you took a cartoon safe, right? Cartoon safe. You take a rope, right? And then on the other side, you put a coyote, right? A very light coyote, and you attach a pulley. What happens when you let the safe go? Yeah, the Cody flies upward, right? Essentially, at free fall upward, right? It should. So what I'm trying to say is, when one of the masses is way bigger, it should essentially just free fall. The other one shouldn't really slow it down, right? What happens to this formula when say M2 is really, really small and M1 is much bigger? Essentially, we can ignore the M2s and we just get M1g over M1, which is just g. So the acceleration is just g when one is way bigger than the other. That makes sense. So there's like a lot of intuitive. What I'm trying to say is, when you're working a problem that has variables like this, it's often useful to think about limiting cases to see if what you're doing is reasonable. Anyway, let's move on to our next example. So we got pulleys, we got boxes, we move on planes, possibly with friction. And then the other thing we like to play with is inclined planes. So here's the inclined plane. And I'll start out frictionless. Let's start out frictionless. You suppose you put a mass here, like so. Then what goes on? If it's on the inclined plane and it's sliding on the inclined plane, if there's no friction, you can ask, what's the acceleration of the box? Right? You know what? I probably should just add friction, given that we don't have a lot of time. So if I'm going to add, let's suppose that the box is moving, so we have kinetic friction, right? That's probably a good idea. We'll add that in a minute. So we're going to assume box moving, and the force due to friction is the kinetic coefficient of friction times the normal force, whatever that is. All right? Okay. So what are the forces acting on the box? We can think about drawing a free body diagram. Yeah, gravity. It's always there, isn't it? Pesky gravity. Can't get away from it. I mean, all these problems become much easier if you put them in a spaceship. It's like, there's no gravity, so there's no forces. It just sits there. It's in equilibrium. Done. What?
Okay, so what is at the bottom of that weird U?
That's a K.
Oh, okay.
And this is a mu. Like,
A mu, okay.
yeah, it's okay. It's the coefficient of static friction. That's its name. Coefficient of static kinetic friction. So, okay, so look.
Coefficient of the kinetic?
Coefficient of kinetic friction, yeah. We will talk about static friction soon. All right, kinetic friction. And I don't want to put any numbers into this example. Let's keep it symbolic to emphasize the way things work without getting cluttered with numbers here. So mg, what does mg look like? Looks like this, right? Gravity is down. Yeah.
Is that an M, like magnetic, or is it magnetic?
That's a K. That's a badly written K. Hey, you're fine. No problem. Please, I do not mind questions. They are helpful. So we've got gravity. And what else? Oh, we got the normal force, right? What direction does the normal force go when you're on an inclined plane? No. So the normal force always points normal. So that's a mathematical term. So the normal to the plane is perpendicular to the plane. The normal force goes like this. So that's the normal force, not to scale. Yes, sir?
I'm having a hard time conceptualizing normal force. Like, nothing's forcing that way, right? Where does that come from?
Well, there has to be a balance of the forces that are perpendicular to the plane, because otherwise, if there was an excess of forces perpendicular to the plane, it'd either be accelerating off the plane or it'd actually be going into the plane. But we know we can put boxes on planes, right? Which means there has to be some sort of balancing between the forces that are perpendicular to the plane. One of those forces is the normal force. Another part of it is the part of gravity which is perpendicular to the plane, which is what I'm about to get to, right? So the part of gravity which is perpendicular to the plane must somehow balance out the normal force in this problem.
So it's like a Newton's third law.
Yes, yeah. But I also think of it as a Newton's second law, looking at the acceleration in the perpendicular direction, like it has to be 0 because it's not accelerating off the plane, right? I mean, we could talk about that, but that would be a really different problem. So this piece of gravity is perpendicular, is my point. What is that? This angle's theta. This angle, well, hold on a second. This angle is theta. This angle up here is theta, isn't it? Because this is complementary to that. Do you guys see that? So this vertical angle right here is theta. And there's a right triangle I can draw eventually. Like this. Listen, I'm going to blow this up. I'm going to blow this up over here. Here's my mg. Because this is important. This is the that perpendicular part of gravity, and here's the parallel part of gravity to the plane, yeah? And so if you look at it geometrically, the angle of inclination for the plane is found up here. So that makes this mg cosine theta, because this is a right angle. And that makes this down here mg sine theta, because it's the opposite side to the angle. This always gets you guys, because you want to think about cosine theta being horizontal and sine theta being vertical, and it's just not the case here. The trigonometry happens to work out so that the part of gravity which is along the plane depends on sine of the angle of inclination, whereas the part going into the normal force depends on the cosine of this angle theta. So again, this is mg cosine theta, and down here we have mg sine theta in the green, and the brown one is the total force of gravity. Gravity, we have to think about decomposing into two vector pieces, the parallel part and the perpendicular part. All right, so I've only talked about the normal force and gravity so far, but we said what? We're also going to think about friction, right? What direction does friction point? If I move this chair, like so, which direction does friction point? It points this way, right? Does it point this way? Does it point that way? No, it points opposite the velocity vector, right? Friction points the opposite direction. So the force of friction, if I'm to draw it up here, is, which direction is this thing going? It's going down, okay. I mean, because you could give the box a shove, right, up the thing, and it could have motion upward. That would be a different question. But you said it's going downward, so great. I mean, I'm not disagreeing. So let's suppose that the motion, my point is that it's ambiguous until we write down. You usually would expect the box to be moving down, but like I said, some cranky physics professor could have pushed it going up before they started the problem just to mess with us, right? Down. So what direction does the friction force go then? Up. Parallel to the plane. So this is the force of friction. So when I'm working an inclined plane problem, my goal is to understand all of the forces perpendicular to the plane and all of the forces parallel to the plane. To solve the problem, I have to understand both. So let's collect our thoughts here. And that's it. That's all that's going on, right? We could add Mr. Top Hat here and have him push on it, right? And he could push on it in such a way that his pushing force, or pulling force, gave yet another contribution to the parallel and perpendicular direction if we wanted to make it more complicated. I think it's complicated enough though, right? Let's stick with this. And so how about this? Perpendicular, and parallel. So perpendicularly, we got what? We got yourself 0, y is 0. Because, again, it's not accelerating off the plane, right? There's an equilibrium with respect to motion along the plane. Like it's not moving into or out of the plane. That's why that has to be 0. And that's also why the normal force has to be mg cosine theta. And then how about parallel? There, we have mass times acceleration, right? Because the acceleration is just along the parallel direction. And now you guys have got to make a choice for me. Right? Do you want down to be positive or do you want down to be negative? Down the plane. Is it a positive or is it a negative? My usual convention is to make it negative, positive in this kind of problem because, like you said, that's the direction of motion. It's a choice. So if we make down to be the positive direction, right? If down is the positive, like this way is the positive direction, then when I write MA, I say MA is equal to mg sine theta, because that's in the same direction as the motion, right? And what about the force of friction? Well, it's the opposite way, right? So minus the force of friction. So my question to you at the moment, I have a couple questions. First of all, do you think that the normal force being mg cosine theta makes sense? Does this make sense? What happens when, what should happen when theta is 0? What should we reduce back to when theta is 0? That's not a, that's like a, it's like the inclined plane in front of you, right? It's not that inclined, is it, right? So what's the normal force if we're just flat? The normal force is just the weight, it's mg, right? And that's what happens. Cosine of 0 is 1. On the other hand, what's the normal force if this inclined plane gets, really extreme, right? Like, suppose the inclined plane is here just to give a demonstration. This could happen. There you go, 90 degrees. What's the normal force? If I put a box on here. Here, let me try. Well, so no normal force, right? As you can see, Oh. I'm now wondering, is this my book or is this Professor Dromby's book? I don't know. Hey, one of you has my book, I think, because I probably loaned you my book. I need my book back. You know who you are. I think I know who you are. Let's see here. Where was I? Oh, yes. So the normal force makes sense, I think. It should be 0 when theta is 90 degrees, right? So we can then solve for this. What does this tell us? MA is equal to mg sine theta. What's the force of friction? Mu k. What's the times the normal force? What's the normal force here? Mg cosine theta, right? So we can find the acceleration. The acceleration is equal to, oh, look at that. What happens here? What happens to m? Yeah. So I don't know if you've been watching TV lately, but if you've been watching any amount of TV, this seems to contradict what I've seen on television. Because there is very clearly a fact that has been seen in many, many commercials, and that is that if a large, overweight person gets on a water slide, right, and they go down that inclined plane, they're going to go much faster than a skinnier person, right? If you've seen many cartoons, it's clearly evidenced that